how does water temperature affect cooling performance? Well, that's something we're going to look at in this video. To do that, we'll be using a GPU. I've got a 2080 Ti with a water block on it that we'll use as our heat source. And something interesting to go back to the roots of water cooling. Some of you who maybe have been around the water cooling scene for a while have used something like this. This is just a plain old aquarium water pump. It does about 370 gallons per hour. That's, about standard what you'd see on a D5 pump these days. A little bit on the low end, but that's fine. This thing can be fully submerged in the water. You throw it in a bucket and it'll pump water out of it. So that was an easy way for me to make sure the water was a specific temperature going into the inlet of this. And then I can have it in an open bucket to have a thermometer in there. So that's why I chose this to use it. 25 bucks on Amazon. And this is how water cooling was done back in the day, before there were all these companies selling water cooling parts that were so easy to use. We used aquarium equipment, and kind of a little bit of a throwback using one of these. So how are we going to chill the water? Well, you may have seen one of these before. Again, this is an aquarium chiller, similar to the kind of chiller that a certain company used to chill their CPUs at an event recently. But this one just chills water using a refrigerant. It uses R134a to chill refrigerant in an internal tank down to a temperature, and it can go down to about 1 or 2 degrees. Below that it'll freeze the water, and you don't want it to get any colder than that. So it's got to stop in here. It won't let it get colder than that. And for our purposes, we went down to about 7 degrees water temperature. Okay, next let's talk about the setup. My standard setup test bench is a 9900K. This one's actually a KF on an Oris Master Z390 board. The 2080 Ti that we already discussed, I use this 24 watt aquarium pump, and it does 370 gallons per hour. So that's real similar to what you'd see in a D5 or a DDC pump in your water cooling kits. And I actually did use a bucket as well. So the way this works is the water comes through the loop into the bucket, pumps in the bottom, pumps back out into the chiller, then into the CPU. The chiller has a thermometer built into it, so I can see the temperature of the water going right into the CPU. And that's how I would monitor it through the chiller, and I would monitor the temperature of the water in the bucket. If those were pretty close, that means the water was stabilized, and I would take the next reading. And it only took a few minutes because this volume of water is pretty small. And this chiller itself is about 5 amps. It does a 1/4 horsepower, and that's enough to chill the water. I got it down to about 7 degrees before we started seeing condensation, and at that point I had enough data. So now next to the data, what did it look like? So I started about 35 degrees. I let it run without the chiller and let it stabilize just how hot it would get on its own. And with the water at 35 degrees and room temperature at about 22 degrees, these are all in Celsius, that had the GPU running TimeSpy Extreme on loop at 44 degrees. So that's a delta of about 9 degrees. And keep that in mind as we go through this, and you'll notice the same thing that I did. And it stayed 9 degrees delta all the way down to chilling the water to 29 degrees. At 29 on the chiller, the GPU was 38. Moving down to 22 degrees on the chiller, we started to see 10 degree delta. So the 22 degrees on the chiller, 32 on the GPU. And then all the way down to 8 degrees fluid in the loop. So right off the chiller, the GPU was reading 19 degrees Celsius. So that's an 11 degree delta. There were a few steps in the delta. It was fairly linear, and it stayed at about 1 degree water per change in temperature to the GPU. But an interesting thing here, it wasn't exactly 1 degree, because at 35 degrees we were seeing a delta T of 9, and down at 7 and 8 degrees we're seeing a delta T of 11. So it was less thermally efficient at the lower temperatures, because we were seeing a greater disparity between the high side and the low side. So that means that slightly less energy was being taken from the GPU, even though it was at a lower temperature. I did monitor GPU usage throughout this, and it stayed at about 300 watts. I let it run until it was stabilized, and using TimeSpy Extreme, I had this thing overclocked to put out as much heat as possible, and kept it at about 300 watts, plus or minus. I let it run for at least 5 minutes to make sure that all the water was stabilized in the loop and we could get good data out of it. So what does this mean? Water loop temperature is one of the factors that can adjust the performance and the overclocking capability of your system. It's very common to see water cooling loops under use being in the mid 40s, about 45, maybe even up to maybe 50 degrees. Much higher than that, it'll start damaging some of the equipment and possibly even hurting your pump. So you don't want to go above 50 degrees, but if you can keep your loops, at 45 degrees, your GPU may be at 50, 55 degrees in that kind of situation, but if you like the trade-off with the noise of the fans that's required to do that, that's just fine. Every degree you bring down, you're going to gain about a degree on your GPU. So that was a lot of setup for this experiment. It ended up being not as interesting as I expected it to be because it ended up being fairly linear, but there are some pretty distinct breakpoints where you gain a degree or two moving to cooler or warmer temperatures. So that's all I have for this one. See you next time.